Hey, I'm Dr. SecuRae. If you're new here, welcome to my channel. If you're returning, whoa, thank you and welcome back. My goal with this channel is to help people understand cybersecurity concepts one small piece at a time. I'm not very fast at creating these videos. I'm a full-time college professor and I do these in my minimal free time. I am also not an artist, as you could tell. I am teaching a computer networks course this semester, so I am going to post a few videos on some of the concepts my students sometimes need to spend a little more time on. I'm usually pretty good at explaining concepts at a very step-by-step pace, so I think I shall give it a go. Thanks, that chapter. One key piece to understanding how devices and software communicate is understanding how we identify each device uniquely. This video is going to assume you have some basic understanding of common network terms, a basic idea of what computer networking is, and why we might use IP addresses. This video exclusively covers IPv4, and I will likely make a video on IPv6 in the future. Computer networking is a foundation skill, and having an understanding of subnetting will assist you in gaining deeper knowledge of how and why network security is applied. If this video sounds like your cup of tea, then today we're diving into the world of networking and tackling a topic that may seem a little intimidating at first: subnetting. Many different methods of subnetting exist, and I hope the way that I explain it in this video helps. If not, please let me know what part you got stuck on and I can explain it in another video. The overall concept sounds easy, right? We take one IP address and we split it up into smaller subnets. It's those darn calculations getting everyone stuck. Why do we subnet? Well, subnetting allows us to efficiently manage our IP addresses, making networks more organized and secure. By dividing a large network into smaller, easier to manage subnetworks, we can enhance performance, reduce congestion, and bolster security measures. Imagine your network as a house. A house which likely has a few rooms labeled or uniquely addressed as kitchen, bathroom, and bedroom. Each of those rooms have a label and are assigned for a specific task, like cooking, showering, or sleeping. Each of the rooms has a specific function, and we equip each of the rooms differently based on need. One room, like the kitchen, similar to a wireless guest network, may be open to everyone, or a bathroom might have a lock on it for privacy, similar to part of the network where proprietary or personal identifiable information is stored. We can manage each of the rooms individually, but they still belong to the house. The house has a main address, so the mail can be delivered and emergency services can locate it if needed. But the public services do not know what types of assets or capabilities are contained within the house, much like virtual local area networks contained in a network, or VLANs. You can secure different parts of the house in different ways because they are separated by walls. We cannot put walls up on our network, so we separate them out by assigning each of our rooms, or VLANs, in my brilliant analogy, and each of the rooms can have different specifications, items located inside of it, just like VLANs can. IP addresses can be divided into two parts. The first part of the IP address is the network portion, and the second part is the host portion. The network portion is the unique number assigned to the network, and it also identifies the class of the network. The host portion of the IP address is the part that can be divided up and distributed between all of the devices on a network. So we're going to take that .0 and change it into multiple IP addresses. The network part of the IP address will be the same for every device on the network, no matter which subnetwork it belongs to. The host part of the IP address is what identifies each device uniquely. How will the devices on the network know which part of the IP address is which? Well, that's where the subnet mask comes in. An additional 32-bit number with the same format as our IP address is assigned, and that number is called a subnet mask. The subnet mask is like a filter, telling us which part of the IP address belongs to the network and which part is available for devices on that particular subnet. The ones in the subnet mask represent the network part of the IP address, while the zeros represent the host portion of the IP address. The subnet mask is not an IP address. It just indicates which part of the IP address is reserved for the network and which part is reserved for the host. If I had an IP address of 192.168.43.0 and a subnet mask of 255.255.255.0, the devices would expect 192.168.43 to be the network portion and the .0 to represent the host. That's great. But how do you and I know that 255.255.255.0 is a subnet mask for 192.168.43.0? It's because IP addressing is managed by IANA, the Internet Assigned Numbers Authority, which provides global coordination of IP addressing. Over 4.3 billion unique IPv4 addresses exist, which need to be managed and categorized to make administering to networks easier. To create some organization, the 4.3 billion IPv4 addresses are categorized into different classes of networks, A, B, C, D, and E. Each class of network is assigned based on the size of the network. Class A addresses represent large networks, while Class C networks are typically smaller. Each letter represents a range of IP addresses. Class A ranges from 1.0.0.1 to 126.255.255.254. Class B represents 128.1.0.1 to 191.255.255.254. Class C is from 192.0.1.1 to 223.255.254.254. Class D and E are reserved for multicast groups, research, development, or other purposes. We will not concentrate on the D and E ranges. Each class is assigned a subnet mask. Class A has the first 8 bits of the IP address reserved, making the subnet mask 255.0.0.0. Class B has the first 16 bits reserved for the network, making the subnet mask 255.255.0.0, and Class C addresses have a subnet mask of 255.255.255.0. The zeros in each of the subnet masks represent the host portions of the IP addresses. You may notice the chart skips 127 completely. Whoa! That's about 16 million IP addresses that are not represented in our chart. That's because the 127 range is reserved for devices. To dig even further, 127.0.0.1 is the default IP address for your network interface card, or NIC. It's also called the loopback address. We can often use it to ping ourselves to see if our NIC is responding. A ping is basically a small signal we send to computers connected to us to see if they would respond. It shows if we have network connectivity. You gamers out there picking up what I'm putting down? If you ping another device and you receive a response, it means you have connectivity and you should be able to communicate. You could try it out. Open up terminal, type in ping, and then a space, 127.0.0.1, and you should receive a response. If your NIC was not working, the request would time out. We will be looking at subnetting example later, so why don't we determine what the subnet mask is now and save ourselves some time. The first IP address we're going to look at is 192.168.43.0, and the second is 172.16.0.0. Starting with 192.168.43.0 and comparing this IP address to our handy chart here, we see that 192 falls into the Class C range, which indicates our subnet mask is 255.255.255.0. Moving over to our next IP, we see 172.16.0.0 falls into the Class B range. So our subnet mask is 255.255.0.0. This means that when we are considering subnetting later, we are only going to be allowed to alter the host portion of the subnet mask, meaning only the zeros in the subnet mask are going to be allowed to be altered. Thinking on 192.168.43.0 with a subnet mask of 255.255.255.0, we now know the first 3 octets of our IP address will remain the same. So all of the IP addresses on our network will be 192.168.43.0.1.2.3, so on and so forth, all the way up through 192.168.43.255. So that means we have 256 IP addresses we can assign to our network devices and client machines, correct? Well, not so fast. 3 of the IP addresses in the range we just identified are reserved. 1 is reserved for the network as a whole. 1 is reserved to be the broadcast address, and 1 is going to serve as our default gateway. These IP addresses cannot be changed, so we make note of them, but we will not be considering those addresses when defining our usable IP range. First, we have to be able to identify the network itself, so the first IP address in the range is always reserved for the network. In this case, it's 192.168.43.0. That's the network address. Another IP address will be reserved for the default gateway. So we will need to have an IP address to represent the entry and exit point of our network, basically from our network to outside networks like the internet. The last IP address in a range is always reserved for the broadcast address. In this case, 192.168.43.255. Broadcast addresses should only be used when a transmission needs to be sent out to all of the devices it is attached to. As you can imagine, this feature could be used excessively and is a cornerstone for some network attacks, which we will talk about in a different video. First, you have to understand how IP addressing works. After that, you can really understand how the online villains might write nefarious programs to take advantage of the way communications and networks behave. Regardless, this leaves us with 253 usable IP addresses in this network. If we want to make our network a little easier to manage and more secure, how will we approach the problem? First, we think about the way we should logically divide the network. On a corporate network, we might divide it into functional areas like human resources, suite, wireless, DMZ, and so forth. I'm going to use a department at a college divided into lab security, wireless, user, and front office as our example. In our scenario, we will need to create 4 subnets. We are going to create a subnet for each of the areas we identified. I have another video explaining how to convert decimal to binary. If you are unfamiliar with that conversion, you should watch that video before you continue. Otherwise, you will miss some important steps, and the rest of this video will not make as much sense to you. The first step is to identify the subnet mask and convert it to binary. So let's start with the IP address 192.168.43.0/24, and we will write down our subnet mask in binary. Earlier, we identified the class as a Class C network in our chart, so here we have 255.255.255.0 written in binary. You will notice we also have a /24 at the end of our IP address. This is called CIDR notation, or Classless Inter Domain Routing. It represents the network bits of an address. In this case, we see we have 24 ones identifying our network in our subnet mask once we have converted it to binary. /24 represents the number of ones we have turned on in our address. So if we had a /8 network, it would indicate the Class A address, right? Because the subnet mask of a Class A address is 255.0.0.0, which would be 1111, with the remaining octets populated with zeros. If you see an address with CIDR notation, it also indicates the subnet mask. So it's an easy way to quickly identify a network. I personally like to have steps to refer to, so I'm going to start by giving you a few steps before we actually begin our first example. I know it won't make that much sense at the moment, but you can always refer back to this to kind of help you remember as we go through so you don't get lost. So, step 1, identify the network class and subnet mask. 2, convert the subnet mask to binary. 3, determine how many host bits are needed. 4, calculate the subnet mask bits by changing 0 to 1 from the left. 5, convert the subnet mask from binary to decimal. 6, find the increment by aligning the last network bit in the subnet mask to our chart. And then 7, create the subnets. The rest of the steps will be doing things like identifying the network address, broadcast address, the range of usable IP addresses, and those are the types of questions that you most often get in like homework assignments or on networking exams. So something that you may want to pay attention to when we get to that part. So now here comes the fun part. We will need to determine how we can assign a range of IP addresses to each of the parts of our network. In our example, we are using a department at a college divided into lab security, wireless, user, and front office. So we will need 4 subnets. How will we get 4 subnets from the .0 part of our IP address? We will do it by borrowing bits from our host range. If we look back into our chart, we see 4 lined up under our second bit from the right. This means we need to change these 2 bits. We do not need them. In our case, we're using a small network as an example, and so we only need to borrow 2 bits. But if we were using a big corporation as an example, and let's say they divided their network into 22 different departments, and then we would need to borrow more bits, 22 bits to be exact. By looking at our chart, we see 22 falls between 16 and 32. So if we were to borrow 4 bits, it would only allow for 16 subnets, max. So in the case of a corporation, they would need up to 32, which is 1, 2, 3, 4, 5 bits. For our much smaller school network, we only need 4 subnets, so we just borrow 2 bits. From the left, we change those 2 bits to 1, and then we are left with the remaining zeros. Now, we convert our subnet mask back to decimal, which will be 255.255.255.192, which ends up being a /26 network. Remember, to get the CIDR notation, all we have to do is count the ones in the subnet mask while it's in binary format. Now we have our IP address 192.168.43.0 and our new subnet mask of 255.255.255.192. But wait, we still haven't actually defined our 4 networks yet. So let's do that next. We have to figure out the best way to split these numbers up, and we do that by finding the increment, which is our last network bit in our subnet mask. Looking at the binary representation of our subnet mask, we see the last network bit is aligned, the last network bit that is turned on is aligned with 64. So we will use 64 as our increment, and it will give us the size of our network and the usable IP addresses we will have available for each. Our first IP address is 192.168.43.0 through 192.168.43.63. It is 63 because we include the 0. Think back to our decimal range. It is 0 through 9 for 10 digits, not 1 through 10. In computing, you will typically start from 0, not 1. So 0 through 63 gives us 64 addresses. The second range picks right up at 192.168.43.64 through 192.168.43.127. Our third range will be 192.168.43.128 through 192.168.43.191. Our fourth subnet will be 192.168.43.192 through 192.168.1.255. Now we have our 4 subnets defined, but wait a minute. We have to further define a few other IP addresses. Our subnet mask for every IP address in all 4 subnets will be 255.255.255.192. So with that in mind, let's dissect our first range, 192.168.43.0 through 192.168.43.63. Earlier, we said the first IP address in the range is always the network ID. Well, that still holds true. So 192.168.43.0 is our network ID. The last IP address in any range is our broadcast address. So 192.168.43.63 is our broadcast ID. That means that the remaining IP addresses, 192.168.43.1 through 192.168.43.62 is the range of usable IP addresses. So how many hosts do we have in our subnets? In this instance, it's pretty easy to look at because we have a very small set, but if you had a larger set, you can always do it like this. Look back at the subnet mask in binary and count the number of zeros. That's the number of host bits, correct? In our case, we have 6 host bits. To determine the number of hosts we have, we can use a formula 2 to the 6, 2 to the number of host bits. So in our case, it's 2 to the 6, which according to our chart is 64. Then we would subtract 2 from that. Why 2? Because one of those IP addresses is our broadcast address, and one of the IP addresses is for our network address. So therefore, 64 minus 2 is 62. We have 62 usable hosts. Our second subnet is in the range of 192.168.43.64 through 192.168.43.127. As before, our first IP address in that range is reserved for the network address, which is 192.168.43.64. Our broadcast address is always the last IP address in range. So in this case, it's 192.168.43.127. And finally, our host range is all of the IP addresses in range. So 192.168.43.65 to 192.168.43.126. The third subnet in range is 192.168.43.128 through 192.168.43.191. Our network ID then is 192.168.43.128. The broadcast address 192.168.43.191. And finally, our host range is 192.168.43.129 through 192.168.43.190. Moving on to our last subnet, in the range of 192.168.43.192-192.168.43.255. Our first address in range is reserved for the network ID, 192.168.43.192. Our last address in range is our broadcast ID, 192.168.43.255. And finally, our host range at 192.168.43.193 through 192.168.43.254. Excellent work! Thank you for watching my video on subnetting. If you have any questions or you would like to request a topic, please leave a comment below. Creating these videos are really fun to me. If you like them too, please consider clicking like and subscribe.